Hey everyone, welcome back. So in this video, we shall look at some of the statistical models that we can use for time series. In particular, we shall take a look at the white noise. So when we want to model a time series, right, what are some of the things to look at? So we want to make sure our model captures different patterns that can be observed in the series. For example, trend, volatility, smoothness. So in all of these examples of time series here, we can see that each has its own pattern, right? This exhibits a certain periodicity. This explosion time series has this increase in volatility around this particular time point. So in this section, we will focus on how to build statistical models to capture smoothness of the time series. So what do I mean by smoothness? So if you look at the top graph, it looks very rough, very choppy, right? So this is what I would call a rough plot. The second one is slightly smoother, right? It's not as choppy as the first one. And the third one is even smoother than the second one, right? So this is what I mean by smoothness. So what does smoothness really say about the data points, right? So smoothness tells us about the relationship between the time series at different points. Smoother plots indicate a stronger relation between points. Rougher plots indicate a weaker relation between the points. So white noise in particular is a time series where all of the time points are uncorrelated, right? So if there is no linear relation between the points, then we call that as a white noise. So to emphasize the point, my point about relationship or larger relationship and smoothness, take a look at this. So the first plot is the white noise. White noise means there is no correlation at all between the time points, right? So you can see that the plot is very rough. In the second graph, I've introduced some amount of correlation. So the graph is smoother. So the smoothness reflects this correlation between the time points. And in the third one, it is even smoother than the second one. And this has a greater correlation than the previous two graphs. So let's take a closer look at white noise. So data points are uncorrelated, that is x1, x2, x3, and so on, right? All of my time points are uncorrelated. We will use the letter W specifically to denote the white noise. So WT, right, which is this white noise time series now, has this mean 0 and the variance denoted by sigma squared W. So a white noise has two parameters, right? First is the mean, and the mean is going to be 0, and the second is the variance. At times, we will require the white noise to be independent and identically distributed. So if that is the case, we will use the letters IID. So WT follows IID. That means it's identically and independently distributed, has mean 0 and variance sigma squared W. So this is a stronger assumption than uncorrelation than points being uncorrelated, right? So independence is harder to achieve than lack of correlation. So specifically, if I say that WT follows a normal distribution with mean 0, variance 1, it means that the time series is independent and identically distributed with this particular or with a standard normal distribution. So the letter W denotes white noise. It means that the time points or the data points are uncorrelated. Sometimes, so if we say IID, that means they're independent and identically distributed. And this N01 means that they're normally distributed. They're independent as well and have mean 0 and variance 1. Now let's visualize the white noise. So the first graph here is white noise. Again, it's centered around 0, so you can see that, right? Variance is 2. In this case, the variance is 1. For this, it's 0.5, and then it's 0.1. So you can see that this variance is reflected on the scale of the y-axis. So when variance is 0.1, right, the range of values for the white noise is pretty small. It's from minus 0.2 to 0.1 roughly. And if the variance is larger, right, that means the scale of values is larger as well. So here's a quick question. Suppose you have a white noise which is independent and normally distributed. Would you use past values? Suppose you have observations from time point 1 to time point 10. Would you use these 10 values to attempt to predict the value at W11? So would you use the past values to predict the future? So make sure you write in your answer in the discussion section on Canvas. So next we'll see how to introduce correlations via moving averages. So white noise is when the data is uncorrelated, right? But in time series, we know that time series typically have high correlations between the data points. So how can we introduce correlations in our model? All right, that's all for this video. I'll talk to you in the next one. Bye.